Hey guys, Mr. Gucci here, and this is going to be your homework help video for the 13.2 gas law worksheet problem. Okay, so what I've done is I've pasted some problems into this little document right here, changed the numbers up a little bit so that they're not the same, changed a few of the units too, but essentially kept the problems the same. Now in this video, I'm going to do the example problem. I'm going to do number 1, number 2, and number 4. So 4 total problems for you to look at. Hopefully this will give you a good idea of how to solve these problems. Now listen, as we discussed in class, all of these problems utilize the exact same equation, and it is this, all right? The exact same equation is this. It is the initial pressure times the initial volume divided by the starting number of moles and the starting temperature equals the final pressure times the final volume divided by the final number of moles and the final temperature. Okay? All of these problems function exactly the same. All you need to do is identify which variables are given, which variable you have to solve for, and which variables are not mentioned. And if any variables are not mentioned, then you cross them out and they are out of the equation. So let's take a look here. So you are told that you have 23.4 moles of gas. That's your starting number of moles. All right, and they are stored in a sealed container at 6.57 atm of pressure. So that's the initial pressure. Okay? A chemical reaction occurs, and now the pressure in the container is 9.32 atmospheres. So that's the final pressure. That's the pressure after. All right? How many moles of gas are now in the container? So you're trying to now find what's the final number of moles. Okay? N2. Yep. So we've got the starting moles and starting pressure. We've got a final number of moles and a final pressure. And what this equation does not mention at all is any mention of volume or any mention of temperature. So because that happens, we assume that these guys do not change. If they're the same on both sides of the equation, then we just eliminate them. So it's P1 over N1, the initial pressure over the initial moles, equals the final pressure over the final number of moles. All right, so now let's plug in what we know. The initial pressure is 6.57 atmospheres. So give us a bit more space right here. Okay, 6.57 atmospheres divided by the number of moles, which is 23.4. And that's going to be equal to the final pressure, which is 9.32 atmospheres, divided by the final number of moles, which we don't know, and we have to solve for. Okay, so what we've got here, guys, is an algebra problem. We have to solve for the number of moles at the end of this. Now, this is a problem where you're solving for the numerator. At this point, guys, this is all algebra, all right? If you're okay with algebra, then, I go and be free and do your algebra. But if you need a little bit of an algebra reminder, and probably more so in this year than ever before, if you have to solve for a value on the bottom of a fraction, this is a key moment to whip out the old cross multiplication. Okay, cross multiply. So 6.57 times n2 times n2 equals 9.32 atmospheres times 23.4. Okay, very good. So now we're doing that. At this point, it's up to you how to solve it. Me, at this point, I want to get n, the number of moles by itself is being multiplied by 6.57. So now I'm just going to divide both sides by 6.57. Divide by 6.57. All right. It cancels out over here, and then we can solve for it on the other side. So here we go. All right. So the final number of moles is equal to 9.32 times 23.4 divided by 6.57. Time to go to the old Google. Let's go, Google. 9.32 times 23.4 divided by 6.57. What I get is 33.2. The number of moles here is 33.2. Don't forget your units. Moles. And that's the answer. Okay, that is the answer right there. So, once again, you start by writing down the complete gas equation. Plug in what you know, delete what's not mentioned, and then solve. Okay, let's try another one. A sample of carbon dioxide occupies a volume of 45 liters at 800 torr pressure. This is very similar to your problem number 1. I've just changed the numbers and units up a bit. All right. So, occupies a volume of 45 liters at 800 torr pressure. What pressure would the gas exert if the volume was compressed to 12 liters? So, once again, I start with the complete gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, what have we got here? This gas occupies a volume of 45 liters. That's the initial volume. And an initial pressure of 800 torr. All right, so that's the initial pressure. What pressure would the gas exert if the volume was compressed to 12 liters? So 12 liters is the second volume. And the pressure we're trying to find is the second pressure. Okay? So we've got the initial pressure and the initial volume, and the final pressure and the final volume. And what's not mentioned here at all? Number of moles is not mentioned at all, so we can delete it. And the temperature is not mentioned at all, so that can also be eliminated. Again, if a variable is not mentioned, we assume that it therefore does not change. And if this is the same number of moles on this side as on this side, that if we're just dividing both sides by the same value, we can just get rid of it. We can assume that it cancels out. All right, and if you're dividing both sides by the same temperature, then we can assume that it's just gone. So what we're left with is P1 V1 equals P2 V2. This is, by the way, that's Boyle's law. That's Boyle's law. Boyle's law is P1 V1 equals P2 V2. These are inversely proportional things, inversely related. So if one goes up, the other goes down. But while other kids have to, memorize this law right here and know when to plug it in, you guys are just doing the clever thing and using the exact same equation every time and just crossing out what's not being mentioned. Okay? So P1 V1 equals P2 V2. So let's plug in the values now. The initial pressure is 800 torr. The initial pressure is 800 torr. The initial volume is 45 liters. The final pressure, we don't know, we got to find it. So it wants us to figure out. And the final volume is 12 liters. Okay? So we're trying to find the final pressure here. Now, guys, we're getting it by itself, which means we just got to undo what's being done to it. Currently, the pressure is being multiplied by 12 liters, so we just got to divide it by 12. Now, I gave you room to do this on the worksheet. You can type it up however you like, but also recognize that this very well could just be easier for you guys if you just write it out by hand. In any case, I do need to see the work because I'm going to give you all the answers. I need to see the work, okay? So show me the work however you see fit, okay? So the final pressure here is equal to 800 times 45 divided by 12. 800 times 45 divided by 12. And what do we get? 3,000. Nice. We get 3,000. 3,000 of what? Now listen, one of the facts that you need to remember for these homework assignments is that you have to have the same units on both sides of the equation. Temperature always needs to be Kelvin. N always needs to be moles. But there's different pressure and volume units that are out there. And you can use whatever pressure and volume units are given to you. But you have to make sure that whatever the unit of pressure is on this side has to be the same unit on this side. Whatever the unit of volume is over here has got to be the same over here. If they're not the same, you have to make them the same. Over here, the pressure is in torr, which means that on the other side, the pressure also needs to be torr. Okay, now that's my sample problem. If your sample problem uses a different unit of pressure, then you have to use that unit. The only constraint is that you have to have the same unit of pressure on both sides. Okay, try another one. Oxygen gas is at a temperature of 75 Celsius when it occupies a volume of 7.6 liters. To what temperature should it be raised to occupy a volume of 17.3 liters? Now, guys, we were encountering something that I made mention of in class, and that's this. Celsius, bad. Celsius, bad. Okay, so if you see Celsius anywhere in here, well, you got to convert it. First things first, I'm going to add 273, and I'm going to turn that into Kelvin. All right, Mr. Gucci's mental math is weak. All right, 75 plus 273 equals 348. Okay, so the actual temperature you're going to need here is 348 Kelvin. Ignore 75 Celsius. The real temperature, all right, the real one is that right there, 348 Kelvin. Okay, bing, bang, boom. Let's see. Oh. Okay, cool. So, this is what matters. All right, not that. Okay, 348 Kelvin. When it occupies a volume of 7.6 liters, to what temperature should it be raised to occupy a volume of 17.3 liters? So once again, there's only one equation in this entire freaking chapter. P1 over V1, P1 times V1 over number of moles times initial temperature equals the final pressure times the final volume divided by the final number of moles times the final temperature. Okay, bing, bang, boom. So let's plug in what we know. We know that the initial temperature is 348 Kelvin. All right, so we have an initial temperature. And it occupies a volume of 7.6 liters. That's the initial volume. So we have an initial volume. What temperature should it be raised to occupy a volume of 17.3 liters? So that's the final volume, okay? And what temperature, there's a final temperature you got to find here, okay? What is not mentioned here, guess what? We did not make any mention of pressure, so we can just ignore that. We didn't make any mention of moles here, so moles can also be eliminated. So we're left with V1 over T1 equals V2 over T2. All right, the directly proportional relationship between volume and temperature. That's Charles' law. All right, that's called Charles' law. All right, V1 T1 equals V2 over T2. Right, that right there, that thing is called Charles' law. But while all the other students in this grade are busy trying to memorize all the laws and their names, you, the clever ones, are just using the same equation every single time and then crossing out the things that you don't need, okay? So, initial volume over initial temperature equals final volume over final temperature. So let's plug it in now. The initial temperature is 348 Kelvin. Okay? The initial pressure, the initial volume is 7.6 liters. And that's going to be equal to, the final volume is 17.3 liters. Clean this up a little bit. 17.3 liters over the final temperature, which is what we are solving for. Now, once again, I'm so sorry, but you have to solve for a denominator sometimes, guys. So once again, we whip out our good friend, cross multiplication. All right, cross multiplication. So the final temperature times 7.6 liters equals 348 Kelvin times 17.3 liters. All right, now again, to solve something means you got to get it by itself. The temperature here is currently being multiplied by 7.6, so we got to divide by 7.6. And then we got to do that over here as well. So the final temperature equals 348 times 17.3 divided by 7.6. Let's see here. 348 divided by, or times 17.3 divided by 7.6. And we get what? 790 2. All right, the answer is 792. What's the temperature unit here? It's Kelvin. It must always be Kelvin. But even if it's not always something, it has to match what's on the other side. All right, and I used Kelvin on this side, which means I got to use Kelvin on this side. That's just how it goes. So there you go. Okay, let's do one more problem. Okay, so that the one that I just did right there, that was equivalent to what your problem number 2 looks like. Okay, now I'm going to do what your problem number 4 looks like, except I just changed some of the numbers. Here we go. Okay, as always, I start by writing the complete gas law. All right, here we go. The initial pressure times the initial volume divided by the initial number of moles times the initial temperature is going to equal the final pressure times the final volume divided by the final moles times the final temperature. All right, now let's plug in what we know. A gas initially has a volume of 890 milliliters. Okay, so guess what volume's mentioned? All right, and a pressure of 350 kilopascals. Okay, so there we go. We got initial pressure. And a temperature of 125 Kelvin. All right, so we got an initial temperature. If we decrease the pressure to 175 kilopascals, so there's a final pressure. Oops, I did the volume. So that's the final pressure. And increase its temperature to 400 Kelvin, so there's your final temperature. What will the new volume of the gas be? So we're looking for the final volume here. And what's not mentioned? Number of moles is not mentioned, so we're just going to ignore that. P1 V1 over T1 equals P2 V2 over T2. Now we're going to plug in what we know. Okay, so the initial volume, 890 milliliters. The initial pressure, 350 kPa. And the initial temperature is 125 Kelvin. Okay. We are going to decrease the pressure to 175 kPa. By the way, the units match on both sides, so we're good to plug that in, okay? We don't have to change any of these units because they're both kPa, all right? And the temperature on the bottom here is increased to 400 Kelvin. What will the new volume of this gas be? So again, we're looking for the volume here, okay? Solving for the volume. Now, to solve for the volume, again, that means we've got to get it by itself, which means undoing everything that's been done to it. Currently, the volume is being divided by 400 Kelvin. Well, how do we undo that? We'll multiply by 400 Kelvin. It'll cancel out over here, and then we got to multiply by 400 Kelvin on this side. Okay? What else is being done to this thing? Well, the volume is being multiplied by 175 kPa. Well, guess what? To undo multiplying by 175, we have to divide by 175 kPa. Bam, bam. And if we divide on this side, then we got to divide on this side, 175 kPa. Okay, okay. All right, so it looks a little messy, but pretty much the final volume is equal to this stuff on the top divided by this stuff on the bottom. Let me just double check this here. I'm going to do this in 2 steps so that I don't make an error. On the top, we have 400 times 350 times 890. So on the top, we get, oh, a big number, big number. On the top, we get 124600000. Okay, big number, makes sense, big number. Then on the bottom, we've got 175 times 125. All right, 175 times 125. We get as an answer 21,875. Okay, So let's just do that. 124600000 divided by 21875, and I get as my answer. Whoa, whoa, whoa! Yowza, 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 yowza. Okay, there we go. 5696. All right, so the volume 2 equals 5696. And now what are the units? The units have to match on both sides. Over here on the left side, the volume units 890 milliliters. So the units we use on this side have to match its milliliters. There you go. Okay. There you go. There's your answer. All right. So there we go, guys. That's how you do it. Again, you start with the same equation every single time. You simply plug in what you know and cross out the things that are not mentioned and then solve. Okay. That's it. It's the same equation every single time. Pro tips. The two things you have to remember are temperature must be in Celsius. You can't have a Kelvin temperature. Sorry. Oh God. Oh God. Back up. Temperature must be in Kelvin. If you see any temperature in Celsius on the worksheet, first thing you do when you open it up, go through, look for all the Celsius temperatures, add 273 to make them Kelvin. Second thing you need to remember, the units have to be the same on both sides. So if you're solving for volume on one side, the units are going to be whatever the volume is on the other side. Okay? Whatever the pressure is, you got to have that on the other side. If by some chance I give you 1 unit of pressure on this side and a different unit of pressure on the other side, you have to convert one of them, doesn't matter which, convert one of them, use Google, I don't care, convert one of them so that the units match. The units have to match. So again, got to use Kelvin, and the units have to match on both sides. All right, guys, I will upload this sheet here for you to look at, and I hope you have a great day. All right, bye, guys.